Here are some notes for my GOB students on lipids. Okay, so the first thing I would suggest is you look at a layout of the land and you realize that there's a hierarchy or an organization chart of lipids where lipids can start from simple components and can add complexity by joining components of chemicals together. So if lipid starts at the top here, so this is the family name, then lipids generally are just hydrophobic. So that means water fearing. So lipids have something in common, they're all water fearing. And the way this, again, we're using some slides from our textbook Flat World, so shout out to them, they're supporting our discussion on lipids today. We can see that lipids are essentially split into not two families here. It's misleading to think that they're families. Lipid is a family name for sure. But the way this diagram is split into fatty acid and steroid, these are two constructs that are built into further subclasses of lipids further on. So if we look at the fatty acid construct, and we'll see what that is in a second, fatty acid construct can lead to these type of lipids, so triglycerides, phosphoglycerides, waxes, and sphingolipids. And then there's another class of structure called steroid, which will go into hormones and other signaling chemicals that we'll see a bit later on. Then if we go down to the sphingolipids, which contain the structure sphingosine, then they can come in two varieties, the sphingomyelins that you might find in a nerve cell. Some people would say that this is biological electrician's tape. I won't, but some people would say that. And glycolipids, which are essentially the prefix glyco essentially means sugar, so lipids that contain sugar structures. And then these sugary lipids are further split into cerebrosides or gangliosides, essentially based on which type of sugar they have, but they are both sugar lipids. Okay, so definitely there's some important vocab in this slide, and it gives you a layout of the land. Okay, so let's start with the first structure, fatty acids. So there's some information here that's useful. Fatty acids, again, this is a chemistry class, so we're interested in the chemical structure of these things. So fatty acids are acids because they contain a carboxylic acid. So recall that a carboxylic acid has a carbonyl, an O, and an H. That's a carboxylic acid. So we know that as an acid, its pH is less than 7. These are weak acids. They're not strong acids, but they definitely can be registered on a pH scale as being acidic. Maybe the pH around 4. That would be a pretty average value. They are carboxylic acids that contain an even number of carbons within a narrow range. So clearly not all carboxylic acids are fatty acids, but all fatty acids are carboxylic acids. So notice this is even. So essentially you could have 12, you could have 14, you could have 16, you could have 18, and 20. And there's a reason for that. The reason for that, just a quick glimpse of the reason for that, it's to do with what fatty acids can be metabolized into. Essentially, fatty acids are metabolized into acetyl coenzyme A, which is a 2-carbon structure. So it's essential that these fatty acids can be metabolized or broken down into units that are 2 carbons in length. And so that's why you won't have odd number carbons, because then you'd ultimately have a 1 carbon unit which can't be metabolized. Okay, we can have different types of fatty acid. We can have saturated fatty acids. We saw in the organic chemistry chapter that a saturated hydrocarbon has a maximum number of hydrogens. So max number of hydrogen atoms, and therefore it has single carbon bonds. Now these have a reputation for being, well, we won't talk about the reputation yet, but they do have a reputation. We can have unsaturated fatty acids. So in general, unsaturated. Now unsaturated, we know, has less than the maximum number of H atoms, and therefore it would have carbon-carbon double bonds, or alkenes. You might have 1 carbon-carbon double bond, in which case you are monounsaturated, so mono means 1. You might have more than 1, you might have many, and the prefix poly just means many. So if you have more than 1, we lump you into the many category, you are polyunsaturated. Okay, so I think we've exhausted that slide of all its goods. So definitely some good vocab in that slide for my students. Let's look at this table here. My students definitely don't have to memorize these names. I certainly don't memorize them. Lauric acid, I am never going to ask any of my students which of the following structures is lauric acid, because in my opinion that's a silly question. That is just a recall of arbitrary fact question. There's no thought that would go into that. But what I might ask my students is, based on the following structures, predict which has the highest melting point. So that structure interpretation and physical property awareness or understanding, that's the type of thing that I'm interested in. So let's have a look at that. So again, we are going to forget these names. They're not important, at least for my students, although another instructor might disagree and think they're very important. So always ask your instructor. Let's have a look at the first 3 structures. So let's look at these 3. They all have these carboxylic acids. They're all fatty acids, and they all have this in common. So we don't have to look at this structure to explain the differences in these melting points. So we're trying to explain, based on the structure, the trending melting point, which goes from lower to higher. So we're not looking for a commonality to explain a difference. We're looking for a difference to explain a difference. So let's have a look. Well, what we notice is we've got more and more carbons. Here we've got 12 carbons total, 14 carbons total. So we've got 12 carbons. Here we have 14 carbons. And here we have 16 carbons. And obviously there's a few more H's because there's more carbons. So we can clearly see a relationship here. We can say that melting point is proportional to the number of carbons in a saturated fatty acid. Why is this? This is because of London dispersion forces. So we can say that this is because of London dispersion forces. Now recall London dispersion forces. London dispersion forces are proportional to number of electrons. So what's the relationship between London dispersion forces and number of electrons and melting point and number of carbons? What's that relationship? Well, clearly we have more carbons and hydrogens, we have more electrons. So this is exactly explained away by an increased London dispersion forces because of a longer carbon chain. Okay. So that's the type of structure physical presentation that I want my students to be aware of. Okay, let's move on to look at palmitic acid versus palmitoleic acid. Again, we're not interested in the names, but let's consider these two here now. They both have 16 carbons. The only difference is this one is saturated and this one, because of its double bond, is unsaturated. We notice that due to that unsaturation, there's a dramatic decrease in the melting point. Dramatic decrease, goes from 63, we just introduce one double bond and it drops to almost freezing point. So clearly this saturated fatty acid would present as a solid because it doesn't melt until it hits 63 degrees. So this would present as a solid, but adding one double bond would make this present as a liquid. Okay. So why is that? This is to do with the density of packing. So let's have a look. I need a little bit of room, so we'll probably go off to the side here to get a bit of space to look at that. Okay, so we will write that for a given number of carbon atoms, unsaturated fatty acids have a lower melting point than saturated fatty acids due to lower packing density. So for example, let's say we have 3 molecules of a saturated fatty acid here. So this is 3 molecules of a carbon 16 fatty acid, let's say. And then we're going to compare that with 3 molecules of a carbon 16. Sorry, I should have said that that was saturated fatty acid, and this one clearly is unsaturated. Okay, Then previously in my class, we've looked at cis-trans isomerization. So predominantly the natural form of unsaturation is cis. So we'll notice that we have cis isomers. This tends to be the common form of isomer found in nature. So we have, it almost make, well, it doesn't almost, it does make the structure bend almost like a V shape. And notice its effect on the London dispersion forces. So if we take, I'll change my pen. If we look at a unit volume, so let's say we look at that volume, and we look at the density in that volume, where density is mass per unit volume. We would have a higher relative density versus if we take the same unit volume. So I've tried to make the blue boxes look the same volume. They just can't get as close to each other because of this kink structure. The density here, which is mass per unit volume, would be lower. So this is what I mean by a lower density and therefore a lower melting point. Because this is lower, it would imply a greater separation. Let's call the separation R of molecules. What does that mean? Well, we know from London dispersion forces that the force of these London dispersion forces is proportional to 1 over the separation squared. This is basically a Coulomb's argument. So if, because of the lower packing density, so less mass per unit volume, that's because the molecules are further apart. So this separation R is going to be greater than this separation R. So if our denominator is greater for the unsaturated fats, then 1 over a large number is a smaller London dispersion force. We have a lower melting point because there's less force to compensate for to separate these molecules and change them from the solid phase to the liquid phase. Okay, so I think we've said enough about that, but that's definitely an important thing to notice in these structures. Okay, so we've looked at the increase in carbon length, we've looked at the change based on unsaturation. Now let's stick with the same carbon length. So let's compare these guys. So we have 18 carbons, 18 carbons, 18 carbons. But now we have, let's see, we have 1 double bond. In this structure we have 2 double bonds. And in this structure we have 3 double bonds. So we're increasing the degree of saturation, of unsaturation. And we can see that the more double bonds we have, the lower the physical properties. Again, that's going to be linking on from our argument here, where we looked at the packing density. You know, you would just have a low packing density if you have 1 double bond, let's say. If you have two double bonds, it would be even worse. Remember, each double bond is typically cis. And then if you had a third double bond, you know, you're just going to be having basically pockets or voids. So again, you're going to have these voids. Where more voids you have, the lower packing density you have. Okay, so definitely our arguments earlier about the number of double bonds, or the presence of a double bond and what it does to packing density, would apply here. So that's how I want you to view that table, not the names of the acids, that's not important, but based on the structure, can we say something, can we predict the melting point? That would be important. Okay, we have essential fatty acids. Other than vocab, you know, an essential fatty acids, essentially, well, pardon the pun, but essentially the word essential means not found, not made, so it's essential that it's in your diet. So just keep a lookout for that vocab word, students of mine. Okay. So let's look at these fatty acids. This slide's nice. It's got the line, ball and line presentation. So if you were in the lab and you were making the structure, you would get your black carbon atoms and your white hydrogen atoms. You've got your carbonyl here with your double bond between carbon and oxygen. Your single bond here. Here's the hydrogen. Here's the acidic hydrogen here. This would be a space filling diagram. But essentially, oftentimes people, myself included, will just draw a squiggle with a head, and that's because clearly you have two features. You have the tail of this structure, which is hydrophobic, and then you have the head. So literally people will say tail and head, which is hydrophilic. So the head will interact with water, great. The tail won't. The tail's bigger, so for the most part, these things don't like water in general because they get bullied by the dominance of the tail. At least when there's one of them. When there's lots of them, it might be a different matter, but when there's one of them, the tail dominates because there's more of it. Okay. Okay, so fats or fatty acids are very abundant in nature. We know that nature prizes fat as a food source. Although fatty acids are not really fat. It's not what people mean when they say fat anyway. If you have a lot of fat in your diet, you're certainly not talking about a fatty acid. You're talking about something that contains a fatty acid, which we'll get to. So let's get to that. Okay. So we've seen fatty acids. These are the things on the left. Fatty acids. Here we've got the organic chemist representation where R is carbon plus other stuff. And then you've got the carboxylic acid functional group here, COOH. Okay, if you take fatty acids, and they can be the same, fatty acids are the same exact molecule, or in this representation we've got R without a prime, R with a prime, and R with a double prime. This is to represent three different types of carbon, of hydrophobic tail. And we take a glycerol structure, which is a 3-carbon unit alcohol, and we can essentially form linkages, basically do a hydrolysis reaction, or an esterification reaction to essentially let's see if I can draw here. So essentially what's happening here is the carboxylic acid group here is being attacked by the alcohol, okay, maybe I can draw this one in blue, and blue, and then blue. Okay. So then the alcohol essentially attacks the carbonyl, and essentially you lose a water molecule. No, I saw you then. Changing the size of my pen without me asking you. Okay. So essentially what I've labeled here in blue, this H2O, this would be the water here. So we do this and we essentially unite that OR with the carbonyl. So we get the carbonyl and then OR. So essentially that happens 3 times and we get this triglyceride. Triglycerides are also known as triacyl glycerol, and this is what we mean when we say fat. So fat, a fatty acid, is not the same thing as a fat. When people say fat, they mean this structure that contains fatty acids, this tri meaning 3, triacyl glycerol. So if you have a high fat diet, you've got lots of triacyl glycerol. If you have a lot of fat in the nutrition label of your snack, it's full of this type of fat. Okay, these types of fats can have reputations. So I alluded to a reputation earlier. So like in our video looking at carbohydrates, there are good and bad, or at least there's a reputation for good and bad fats. Sorry, a reputation for good and bad carbohydrates. Let's take a second to discuss the reputation, however ill-founded, of good and bad fats. So I'm going to say by reputation, that doesn't mean it's accurate. By reputation, a bad fat means saturated, and saturated fats typically have an animal source. And again, by reputation, a good fat is an unsaturated fat, which typically has a plant origin or a fish origin. So think of an oily fish or a plant fat like flax oil or fish oil versus animal fat like bacon grease, that type of thing. Again, this reputation, you know, if you were to, I don't know what happened with my, I'm not sure what happened to my A over here. There you go. If you were to sit on your couch watching TV, eating salmon all day, that would be bad. If you sit on your couch for 5 minutes, have a greasy piece of bacon, and then go out and run a marathon, you probably would lose the argument that that's bad. So again, be very cautious about these reputations. I think the badness doesn't come from the chemical. It comes from the behavior of the consumer of the chemical. But anyway, it's good to be aware of these reputations. And now we can see that these so-called bad fats have 3 fatty acids, none of which are unsaturated, all of which are saturated. And the supposedly good fats, at least one of the fatty acids has to be unsaturated. So you don't need all 3, but if you have at least one double bond in your fatty acid, then the whole structure is unsaturated, and suddenly people say that that is good. So be very careful of reputations. I think there's a lesson there. Okay, I think we're good with that slide, so let's move on, onwards and upwards. So fats and oils, what's the difference? Typically, the good fats present as oils, which means they're liquid at room temperature. Why are they liquid at room temperature? Recall our discussion about packing structure. So you can go back in the video and look at our discussion about packing structure. You're an oil because your melting point is below room temperature. So you've already melted to the liquid phase. And why did you do that? Well, the fact that you have double bonds and they're cis means that your density of packing is lower. Your London dispersion forces are therefore weaker. So there's less energy required to separate you into mobile molecules in the liquid phase. And that energy is provided adequately at lower temperatures. Fats tend to pack closer together. If they are saturated, greater than room temperature conditions are needed to make them mobile, so they tend to present as a solid. We know that oil floats on water. You know, if you've ever been to a restaurant and you've had some olive oil and some vinegar, you know that the olive oil floats on the top and denies you access to the vinegar, which is all that you really care about. Or if there's a natural disaster at sea and oil spills, we know that the oil tends to float around for a long time before weathering does anything to it. Why are they poor conductors of heat and electricity? I don't know if we want to go there in this topic. I mean, all I would say, because it's not that relevant to what we're talking about, but I would consider the fact that it's not a metal. We don't really study metallic bonding at the GOB level, so it's hard to compare it with a metal because we don't look at metals. But certainly we could say that These structures are long, and the electrical signal just gets lost in the long structure. There's lots of places it can get lost. That's my way of glossing over. That's my way of not putting a fine point on it. And I've kept that deliberately abstract because it's just not something we would discuss at this level. So it's more anecdotal. I guess that's what I'm trying to say. Okay, just speaking of anecdotes, this type of course, we tend to mention the proximity, again, in terms of structure, not really of chemistry, but in terms of structural integration, we tend to mention soaps at this stage. So saponification is essentially the process by which you could make soaps. I'm less interested in the chemistry of saponification. I'm more interested in why soaps work. So if you look at a fat on the left, so I will get my red pen. We have a fat over here. So this is a fat, and we know that it's hydrophobic. It's greasy. You can't just wash it off with water alone. But if we take that fat, and the reason why you can't wash it off with water alone is because of these long carbon chains here. Remember, hydrocarbons don't like water. So if your structure is dominated by 3 long hydrocarbons, you're basically telling water, hey, most of me doesn't like you, so stay away. And so water will stay away. So the fat tends to interact with its other fat buddies, and the water tends to be left out in the cold and can't interact with the fat. Okay, so if we break down the fat into its fatty acids, so these are just the fatty acids now. So we've gotten rid of the glycerol unit, and we've now just got the free fatty acids. And then if we add base, so this is just a base, sodium hydroxide, then we know that we've got an acid and a base. Well, we know this is a neutralization reaction. This is going to give us salt and water. Well, the soap here is the salt of the fatty acid. So here the soap is the salt of the fatty acid. So the soap is the salt of the fatty acid. So we've essentially replaced the acidic hydrogen with, so basically H plus left and Na plus replaced it. And remember, by definition, salt here, I'm not looking at the acidity of a salt. I'm just going to say in general a salt is neither an acid nor a base. At this level, that will suffice. Why would this soap then why would it then interact with the fat? Well, now the soap has got lots in common with the fat. I've got exactly the same hydrocarbons that you have. So if I then put the soap on that fat, all of these hydrocarbons are going to have lots in common with all of these hydrocarbons. They're going to bind to each other, and so I've anchored the soap molecule in. And then this part of the soap molecule, this part here, that's going to have lots in common with water molecules, because water loves charge and it loves oxygen. So the water drags this part of the soap molecule away, and then the hydrocarbon part of the soap molecule drags the fat with it. So you're essentially enabling, it's almost like a corkscrew. You know, you've corkscrewed the soap molecule the tails of the soap molecule into the fat, and then you've pulled the head away, this charged part of the soap, and it kind of drags the greasy fat with it. So that's how soap works, and that would be an important structural recognition of the soap molecule. Let's not discuss waxes at this stage. Oh, actually, it looks like that's probably the only thing that's mentioned about waxes. The only thing I'll say about waxes, well, not the only thing. So let's say a few things, all right. Let's say a few things about waxes, for goodness sake. Okay. So waxes are essentially esters. Now an ester in organic chemistry has a carbonyl. It has an R group, an O group, and then another R group. The R's can be the same or they can be different. But if your R group's a long chain ester, but importantly it has this ester group sandwiching the two R groups, then that would be a wax. You could synthesize a wax from a fatty acid. So you could take, for example, a fatty acid. You could take an alcohol. Let's make that part blue. Let's make this part blue. The oxygen could attack the carbonyl, and essentially you are going to, let's stick with black again. You would essentially lose this water molecule here. We're not really interested in the mechanism here. We are interested in having an arrow rather than a plus sign though. Nope. Okay, so I want that one, and I want an arrow, there you go, and I can have essentially my ester, or my wax, if it's long enough, plus my water molecule. Okay, so we can form esters from alcohols and carboxylic acids. My highly responsive tablet here. So carboxylic acid, and alcohol to give an ester and water. And likewise, this could be reversible. Again, under what conditions can you make this happen? That's not part of our course, but we just want to be aware that we can interchange these functional groups. We could have water and an ester to give a carboxylic acid and an alcohol. How could you monitor this? Well, if you were on the left here, you would have a pH less than 7. And if you were on the right here, you would have a pH a lot closer to 7. Depending on what type of ester you had, but it would be a lot closer to 7. So you could use pH to monitor this process. Okay, so that's probably all we need to know at this GOB level about waxes. Okay, we're at 45 minutes. I try and keep these videos around an hour max. We might have to do more than one. We'll see. I try not to go over the hour though. Okay, so Throwback Thursday. Animal cells, plant cells. Here we have an animal cell. This is not a biology course, so we're not really interested in naming these structures within a cell. But we just want to point out that there are substructures within a cell. These substructures are called organelles. And most, if not all of them, have membranes. So essentially we're moving now to talk about membranes, or the type of fats that are used to give us membranes. And this might actually, because there's a pivot now, this might be a good place to stop this video in hindsight or in foresight. Okay, I think we'll do that. We'll wrap this video up and I'll make a second video where we'll look at membrane, lipids, and steroids. So stay tuned.